Hello everyone, my name is Taha Hussein. Today we will be talking about the life cycle of a low mass star. Before I go over the different phases a low mass star experiences in its lifetime, I would like to define stellar evolution. Stellar evolution is the process by which stars experience evolution over a course of time. Although stars do not seem to change much over the course of a few years, this is because the entire life cycle of a star can last millions if not billions of years. Over this long period of time, a star experiences different states or stages during its lifetime. So today we will only be going over the different phases of a low mass star, which is different than the stages of a high mass star experiences over its lifetime. One important thing to note is that space isn't completely empty or void, rather it contains tiny clouds of dust particles which are mostly composed of hydrogen and helium. The process of stellar birth begins with the formation of molecular clouds. Usually these clouds have lower temperature and higher density. Not only are these clouds made up of gases, they also include interstellar dust. Interstellar dust is mainly composed of molecular hydrogen and helium. These clouds are what can be said as the pre-star development phase. The formation of a star is caused by a reaction between gravity and the molecules, causing the core to generate more heat. Once the star has reached adequate temperature, the core will become somewhat stabilized. As a result, this cloud has formed a protostar, a mass of gas that has developed to have some characteristics of a star, and has not yet become a fully fledged star. So what will happen next is a protostar will begin developing over time to form a main sequence star. So how does this happen? When the nebula of a gas molecule begins to join together in the protostar stage, due to the concentration of mass in the center, resulting in an increase of gravity. In order for the protostar to gain adequate gravitational force, there must be enough mass in the nebula to feed it. The gravitational pull grows as the protostar gains mass, causing gas molecules to collide and heat up. The combination of gravitational force and heat creates ideal conditions for elements with light nuclei such as hydrogen to be squashed together and fused. When a proton and neutron hydrogen nuclei fuse with another hydrogen nucleus, helium with two protons and a single neutron is formed. The energy of the missing neutron is released, and nuclear fusion events release enormous amounts of energy as heat and radiation. Once the star reaches high enough temperature to maintain nuclear fusion, it has converted to a main sequence star. A main sequence star is the phase of stellar evolution that a star maintains for a long period of time. Over this course of time, the star burns out its hydrogen until there is nothing left. The lifespan of a main sequence star is said to be somewhat uneventful, as the star lives most of its life in this stage. A low mass star can live up to 80 billion years in the main sequence. The time a star stays main sequence is primarily dependent on its size and core temperature. The more massive the star, the hotter the star is. Thus, it lives in the main sequence for a shorter period of time in comparison to a smaller, less massive star whose temperature is lower. This is because the higher temperature stars are able to burn through hydrogen molecules at a significantly faster rate than those with lower temperature. One side note is that the color of stars are used to indicate the overall temperature of a star. Because the low mass star has relatively lower temperature in comparison to higher mass stars, the colors of lower mass stars are scattered between red, orange, and brown. So how does a main sequence star become a red giant? So before we go over that, I would like to define what a red giant is. A red giant is a star that has exhausted its hydrogen supply in its core that is over 100 times the mass of a sun. A red giant is formed when a low mass star reduces the number of independent particles within the core. Usually this fusion reaction converts 4 protons into 1 helium nucleus. As a result, the core size will gradually decrease until all of the hydrogen has been used in the process of thermal fusion. Once the core is depleted of hydrogen, the process of nuclear fusion will cease within the core. As a result of this process, gravity begins to collapse the core once more. As the core size decreases, the outer layers of the star expand in addition to a significant increase in the luminosity of a star. Once the star reaches a certain temperature, approximately 100 million Kelvin, and a certain density, the star will start the process of fusion, but through helium rather than hydrogen. The helium nuclei in the star begin to fuse with carbon, allowing the star to maintain the stability in its core. So life as a red giant. Throughout a star's lifespan as a red giant, the outer layers of a star will increase in size while the core will continue to shrink. We can take the example of what is predicted to happen to our sun to better understand this concept. But before this, we must understand how that the sun's core is now made up of helium, and the outer layers consist of hydrogen molecules that have not yet experienced the process of fusion. Due to gravity, the hydrogen molecules will shrink and gain enough heat to undergo the process of hydrogen shell fusion. The energy produced by this fusion will result in a buildup of thermal energy in the outer shell. This will push the surface outwards until the luminosity matches the rate of fusion. This process will continue throughout the star's life as a red giant. So after approximately 100 million years, the red giant fuses all of its helium molecules into carbon-fused molecules. As a result, the core no longer has a source of fuel to continue the process of fusion. It will cause the core to become unstable a third time. In addition, gravity will no longer be able to contain the expansion of the star's outer layers, as it will eject these layers into space. What remains is a carbon ionizing the gases in an expanding shell, allowing it to glow brightly. And this has formed a white dwarf star. Following the dispersion of the outer layers of a star, all what remains is a reduced core primarily made up of carbon-fused molecules. The core emits ultraviolet rays with a core temperature of around 100,000 Kelvin, allowing the white dwarf to glow. As time progresses, the white dwarf will begin cooling, resulting in the loss of its luminosity, thus cannot be seen anymore, emitting no energy. This is the end of a life cycle of a star's life and is called a black dwarf. Thank you so much for watching the video, and I hope you guys learned about the life cycle of a low mass star.